In our last video, we talked a little bit about how to take determinants in the 2x2 and the 3x3 case. And in this video, we're going to take it a step farther and kind of offer a geometric interpretation of the determinant and show a couple of examples of how this pops up in a 2x2 and a 3x3 case. So first, I just want to say that, just to overarching this whole thing, the determinant gives kind of like a notion of area or volume as defined by the vectors that you're working with. So in particular, the determinant gives area or volume of the parallelogram or parallelepiped that has edges that are given by the vectors that you're working with. So what does that mean? Let me just draw a couple of pictures. When we're working in like a 2D case, parallelogram, that's when we're going to talk about an area. So we're looking at 2D vectors, say u equal to ux v or uy and v equal to vx vy. Then the parallelogram that is given by these two vectors might look something kind of like this. So if we have these two vectors v and u, then you can kind of imagine completing a parallelogram by using these vectors. This is just like a second copy of u and a second copy of v. And it's the area of this particular parallelogram that is defined by these two vectors that the determinant gives you when you kind of squish these two vectors together into a 2x2 determinant. So that's going to be equal to the determinant of, we take our vector u and put it in the first row here, and their vector v and put it in the second row like that, and we take its determinant, and that gives you the area. And if we want to look in the 3D case, we get a parallelepiped. So say that we have, again, u, but this time equal to ux, uy, uz, v equal to vx, vy, vz, and then we're going to need a third vector, w equal to wx, wy, wz. And the parallelepiped that's defined by this is, it's a similar definition as the one for the parallelogram here. If we have our vector u and our vector v, and then we have the third vector, say a w, and it goes back something kind of like that. So that's w, u, v. Then by kind of, we can imagine that this defines an entire parallelepiped, or maybe you want to kind of think about it as like a parallelogram styled prism. It would look something kind of like this. This drawing may be a little bit rough, but basically we just define a few more copies of the vectors that we're starting with, and we wind up with this three-dimensional solid that has edges whose lengths are given by u, v, and w. And it's this particular volume that is given by the determinant. And that's going to be the same idea as up here. We take those vectors and we stack them into the determinants by row. So ux, uy, uz is the first row, vx, vy, vz is the second row, and then w is going to give us the third row. So this number that you get out of this determinant gives you that entire volume defined by the parallelepiped from the vectors. Let's work a couple of examples. The first example that I'm going to do is going to be a parallelogram. So that's going to be our two-dimensional case. So we're going to find the area of the parallelogram with sides that are given by u equal to 3, 1, and v equal to -2, -4. So in order to do this, the area is given by the determinants that is created out of these two vectors. So we just kind of stack them into our determinant here, 3, 1, -2, -4. So u went into the first row, and then v is in the second row. And we just take the determinant of this guy right here. And since it's just a 2 by 2, we can go ahead and apply our diagonal rule. So we're going to get 3, -4 minus 1 times -2. So simplifying that down, you're just going to get -10. So what that means is that the parallelogram with edges u and v has area equal to -10. Okay, so again, that's just finding the area of this parallelogram right here. This isn't an exact drawing, clearly, but we just found this area. Okay, so this is just in the 2D case. Let's do an example in the 3D case. In this one, we want to find the volume of a parallelepiped with edges that are given by u equal to 0, -1, 2, v equal to 3, 2, and 5, and w equal to -6, 7, 8. Okay, so in this, same idea as before. We just take these three vectors, we stack them into our determinant bars here, and then we'll take the determinant, and the number we get is going to be the volume of that parallelepiped. So u is going to go into the first row, 0, -1, 2. V goes into the second row, 3, 2, 5. And then W goes into our third row, -6, 7, and 8. And we're going to take the determinant of this following the same rule that we did last time, where we go through each one of these and use them as the coefficients on the determinants of what's left over when we cross out their row and column. So for this first one here, we're going to look at 0 as being our first coefficient there. Now we're taking the determinant of what's left here, and that's going to be the 2, 8, 7, 5. But because we're going to multiply it all by 0, it really actually doesn't matter what's in there. So I'm not even going to fill it out. For our second one though, we have minus, because remember we swap signs, plus, minus, so on and so forth. And then the -1. And we want to look at the determinant of what's left behind when we cross out the row and column from that. So that's going to be the determinant of 3, 5, -6, 8. So we're going to have 3 times 8 for that first diagonal, minus 5 times -6 for that second diagonal, and then close the parentheses there. And then finally, we'll add to it 2 times the determinant of what's left over there. So we're going to get 3 times 7 minus 2 times -6. Just like so. All right, so just to finish up this volume, all you got to do, put that all into your calculator, or compute it by hand, whatever floats your boat, and you're going to get 120 as being the volume of the parallelepiped that has these those edges. So and that's all there is pretty much to this big idea. Once again, You just take the vectors that you're working with that define the edges of your shape, stack them all into the determinant bars, take their determinant, and then the number that you get is what you're looking for. And that's pretty much it for this video. Thank you for watching.